At this point in the lecture course, we've just completed a remarkable tour through the universe. In addition to meeting a wonderful array of astronomical phenomena, we've also been able to explain almost everything, at least in broad outline, from the first microsecond to today. And we even think we have a good idea of what the future will bring. This entire story comes under the title, The Standard Hot Big Bang Theory. In many ways, it's an incredible success story, and it undoubtedly contains a great deal of truth. But, and this is an important point, ever since the 1960s, it's been known that the theory is seriously lacking in a fundamental way. It's not that the theory gets anything actually wrong, but it's thoroughly unable to explain several key properties of the universe. For example, it can't explain why the geometry of the universe is Euclidean or flat. It can't explain why the universe is so smooth on large scales. And it can't explain why the universe has some lumpiness on smaller scales. Now, cosmologists refer to these three problems as the flatness problem, the horizon problem, and the structure problem. So my aim in this lecture is to explain to you what these problems are and why they really do demand an explanation. Now, providing that explanation is what the next three lectures are all about, and it's in those that we'll be talking about inflation. You see, what's badly lacking in the standard Big Bang theory is a launching mechanism, some way to get the expansion going. That's what inflation is all about. It launches the expansion. And as we'll see, it does it in exactly the right way to explain why the universe is so flat, why it's so smooth, and yet why it has some structure. So inflation is really a remarkable addition to the whole subject of cosmology, and it elevates the standard hot Big Bang theory to the inflationary hot Big Bang theory. So let's start off looking at these worrying problems for the standard theory, beginning with the flatness problem. So remember, the universe's geometry has now been measured, and we find it to be accurately Euclidean. So the angles inside billion light-year triangles add up to 180 degrees, just like they would for small triangles on a flat piece of paper. Now, to understand why this might be a problem, it's important to remember that what really makes the universe's geometry flat is that its density is equal to its critical density, which is itself given by this equation, which includes Hubble's expansion constant and Newton's gravitational constant, big G. So, with these in mind, you might not be surprised to hear that there are in fact three equivalent ways to state the flatness problem. Why is the universe's geometry flat? Why is the universe's density equal to the critical density? And why is the universe's expansion speed equal to the Newtonian escape speed? Now, I'll come back to that last one in a minute, but these three all amount to the same thing. Now, you may be wondering, why shouldn't the universe have these conditions? They seem reasonable enough. But in the standard theory, they're not reasonable, because they are unusually special. They're each on a knife edge between two quite different situations. The puzzle is, why sit on the knife edge when anywhere else might do? But perhaps it's just luck. After all, the data say the universe is only about 1%, within 1% of these conditions, so perhaps the knife edge is broad enough for us not to worry. But the answer is no. We should worry for the following reason. The precision of the conditions, the width of the knife edge, was finer in the past. See, if the universe is within 1% of flat today, it was within 0.1% when it was 10 times smaller. It was within 0.01% when it was 100 times smaller, and it was within 1/1000% when it was 1,000,000,000 times smaller, about a minute after the Big Bang. So at early times, the knife edge was incredibly sharp, and the universe was sitting right on it. Why? Now, to help you see why the knife edge was thinner in the past, I'm going to develop that third version of the flatness problem. The universe's expansion speed is close to the Newtonian escape speed. It comes directly from Lecture 11, when we modelled the universe as an expanding sphere of rocks. When the rock sphere had critical density, the rocks moved out at the escape speed. They neither fell back down nor zoomed off to infinity. They were on the knife edge between those two. So, imagine you're standing on the Earth's surface where the escape speed is about 10 kilometers per second, and you launch a rock upwards, almost but not quite at the escape speed, just 1% slower. Now, ignoring air resistance, it would go out about as far as the Moon before it stopped, turned around, and fell back down. Now, ignoring dark energy for a moment, that's basically the condition that the universe is in. It's expanding within about 1% of its escape speed. Okay, so now let's imagine going to an earlier time, when the universe was 100 times smaller than it is today. In our model, we need to imagine the Earth crushed down to 100 times smaller. There it is, about 80 miles across, but with the same mass. So the gravity at the surface is now really strong. You weigh 1,000 tons, and the escape speed is 100 kilometers per second. Here's a question. How fast do you have to launch the rock upwards, still just to reach the Moon? The answer is 0.01% below the escape speed. That's less by just 10 meters per second. If we'd launched it at 1% below the escape speed, the rock would have only gone up 2,000 miles before falling back down. Let's just push this more extreme to when the universe was 100 millionth of its current size, about half an hour after the Big Bang. Matching to our model, the Earth is now the size of an orange. The gravity is incredibly strong, and the escape speed is 100,000 kilometers per second. That's a third light speed. To reach the Moon this time, we need to launch our rock at just 100 millionth of a percent below the escape speed. That's an ant's walking speed, slower than a third light speed. If instead we'd launched at 1% below the escape speed, the rock would have reached 3 meters before falling back down in about a microsecond. If we'd launched at 1% above the escape speed, the rock zooms past the Moon at 1,000 kilometers per second. So basically, the gravity is so strong, it's exceedingly difficult to throw the rock at just the right speed. Not quite enough is hopeless. A bit too much ends up being way too much. So now do you see why this is a puzzle for the standard hot Big Bang theory? In order for the universe to get so big, at very early times it must have been expanding at a speed incredibly well matched to its escape speed. And the standard model has no explanation for the simple reason that it has no launching mechanism. And with no launching mechanism, such a fine-tuning is just a complete mystery. Now, of course, what we learn from all of this is that whatever it is, the launching mechanism must somehow hurl the universe's expansion at exactly the escape speed. Now you can see why a simple explosion metaphor for the birth of the universe is very misleading. A real explosion would never result in everything moving at exactly the right speed. The launch must be a much more subtle process than simply just a Big Bang, to use Fred Hoyle's original derogatory phrase. Let's quickly look at the second version of the flatness problem, which looks at density rather than expansion speed. Here are the expansion curves for 3 universes that begin to diverge after about 1 billion years. But if we take each of these universes back to a nanosecond, these were their densities. They're all extremely close to the critical density at that time, and they differ by just 1 gram per cubic centimetre. So universes that are fairly close to the critical density today must have been incredibly close to the critical density in the early universe. Once again, the Standard Model can't explain why the actual density in the early universe was so close to the critical density. Now, it turns out there is a single, simple reason why the Standard Model has such a hard time with these problems. Its early expansion was decelerating. This is extremely important, so let me take a minute to explain it. Here's a graph that's going to show how omega changes with time. In other words, how the ratio of the actual density to the critical density, that's omega, how that changes as the universe expands. Let's pick a particular time and mark it with a little naught. And at that time, the value of omega is omega naught. Let's say it's 0.8. The universe is slightly below critical, which itself is marked by a dashed line. Now here's a graph showing the expansion speed, the speed at which two regions are separating. Now from lecture 12, remember that as long as the early universe is dominated by radiation or matter, then the expansion decelerates, like the green curve, passing through V0 at our reference time. Now here's the equation that tells us how omega changes. I don't have time to derive this for you, but it's fairly simple. Omega is 1 minus the ratio of 1 minus omega naught over V0 squared. So if omega naught is 0.8, the top part you can see is 0.2. Now let's go forward in time. V0 decreases because we have a deceleration. So our ratio increases, so 1 minus the ratio decreases, and we see that omega decreases, moving away from unity. Now the same thing happens if we start with an omega naught greater than 1. Let's just say 1.2. So that the top of the fraction is then minus 0.2. So omega also moves away from unity, but this time increasing. So here's just a summary of that math. As long as the expansion is decelerating, then the universe evolves away from having critical density, away from being flat, away from moving with the escape speed. This creates the flatness problem. Because the universe must have been born incredibly close to flat to still be flat today. And that's the mystery. Now at this point, I hope you're beginning to guess at a possible solution to this problem. If decelerating expansion drives the universe away from flat, maybe accelerating expansion drives it towards flat. And in fact, it does. Here are the exact same curves, but for an accelerating expansion. V0 now increases, so the ratio goes to 0, so omega rapidly converges on 1. So we have one of the characteristics of a possible launching mechanism. As long as it involves a period of accelerating expansion, we can ensure that the universe is launched at its escape speed, at its critical density, and accurately flat. And as I'm sure you've now realized, of course, inflation does exactly that. So now let's turn to our second major problem for the standard hot Big Bang, the horizon problem. This can also be stated a few ways. Why is the universe so smooth and homogeneous? Why is it the same at all locations? In other words, why does it obey the cosmological principle? Now, just as before, you might be thinking, well, why not? But here's a simple reason why it's puzzling. Way off over there, 13.7 billion light years away, sits a piece of the microwave background. And way off over there sits another piece of the microwave background. Now, the radiation from one side has only just reached here. So there is no way that that piece could ever have communicated with that piece. In the standard hot Big Bang theory, those two patches on opposite sides of the sky have never been in contact, ever. So why are they so similar? You see, normally we only expect things to be similar if they've had a common origin, when they were sufficiently in contact to make them similar. Here's an example. On all the world's continents, human beings are exceedingly similar, physiologically, genetically, and psychologically. Now, it's just not possible that they've all evolved that way independently. The degree of similarity points to a common origin, a time perhaps a few million years ago in Africa when a relatively small gene pool was homogenized. Now, you may be thinking, that's actually quite a good metaphor for the universe. After all, everything was all together in the Big Bang. Everything was touching. Perhaps that's when the conditions were homogenized. Well, that would be okay if it wasn't for a rather curious feature of the standard hot Big Bang expansion. Because it's dominated by radiation at the beginning, then the Friedmann equation tells us that when it was born at time equals 0, it was, and this is the important part, expanding infinitely fast. Any 2 points, no matter how close together, at that first instant, were moving apart with infinite speed. And that seriously affects the way any smoothing can occur. So let's follow how this smoothing does in fact occur in these circumstances. Here are 2 points, A and B, an instant after the Big Bang. B is a distance, SB, away from A, and is being carried away by the expansion. Meanwhile, forces can propagate away from A at roughly light speed and have reached a distance, dH. Cosmologists call this the horizon distance. Basically, A can't see or feel anything beyond the horizon distance. There simply hasn't been time for light to cross a larger distance. So the key question is, has B ever been inside A's horizon? Could it ever have been in contact with A? Well, let's look at how the graphs of these two distances grow with time. Here's the steady growth of A's horizon, dH. It grows proportional to time, getting bigger at roughly light speed. Now here's the separation, SB, between A and B. Remember, in a radiation universe, the expansion is proportional to the square root of time. So it starts out with infinite speed, but rapidly decelerates. So the line rises fast, but then curves over. So at later times, when the expansion decelerates, the horizon can catch up with B and includes it. And after that, A and B are in causal contact. But what about at earlier times? Was B in contact right at the beginning? Now, I know these graphs make it look like they cross at the Big Bang, but that's deceptive. Here is exactly the same diagram, but using exponential axes, which allow us to examine the region very close to the Big Bang. Now you can see that it doesn't matter how close to the Big Bang you go, the horizon is always smaller than the separation. Nor does it matter how close the 2 points are. At the very beginning, nothing is in contact. Everywhere is utterly independent. This rather bizarre situation leads to a very important prediction for a standard Big Bang universe. At any given time, the largest distance across which one expects to find coherent, smooth properties is the horizon size, which is roughly the speed of light times the age of the universe. So let's test this prediction with the microwave background. At that time, the horizon size was about 400,000 light years, which appears about 1 degree on the sky. Well, here's the all-sky microwave background image with a 10-degree square. So the prediction of the standard Big Bang is that the microwave background should be smooth within each of these little 1-degree regions, but not between them, since they've never been in contact. Well, of course, this is absolutely not the case. The microwave background is famously smooth within 1 part in 100,000 across the entire sky. So the whole situation is a bit like the following. Arriving at an airport to find that all 600 passengers are wearing the same outfit, same shirt, same pants, same shoes, same everything. Now, to a standard theory of sociology, this would be very puzzling. Normally, people on a plane have never met each other before, never been in contact, so there's no reason everyone would wear the same outfit, and yet they do. Now, in this situation, we'd need to revise our sociology theory and conclude that there had in fact been some prior contact in which they'd all agreed to wear the same outfit. So what feature of the standard theory of cosmology is at the heart of the horizon problem? What needs changing? Well, just as we found for the flatness problem, the weakness is in the initial launching condition. The reason for a causally disconnected early universe is that the expansion starts fast and decelerates. You can probably guess how to solve the problem. What happens if, instead of following the standard curve right back to the beginning, there was an initial period in which the expansion starts slowly and then accelerates? This time, right from the beginning, the horizon is larger than the neighboring regions, and so homogeneity can quickly be established. Expansion then takes this homogeneous region and blows it up huge. Bingo! We have a huge homogeneous universe. This is, of course, exactly the kind of inflationary launch we'll be looking at next lecture, but I wanted you to see how it solves the horizon problem here in this lecture. Okay, let's now look at the third major problem with the standard Big Bang theory, what's called the structure problem. Basically, we need a mechanism to generate slight roughness in the early universe so that stars and galaxies can then form. And the standard Big Bang cannot do this. In fact, as we've just learned, if anything, the standard Big Bang generates a wildly lumpy universe because everywhere is completely independent at early times. But even if, for some completely unknown reason, the universe was born completely smooth, then that's still no good, because the standard model is incapable of generating roughness out of smoothness. The most it ever has to work with are the small statistical variations in the number of particles from place to place, and the inherent variations of all quantities due to quantum mechanics. But in the hands of the standard Big Bang, neither of these types of roughness is large enough to get picked up and amplified. What's needed is some mechanism, possibly part of the launch itself, that somehow introduces the right amount of roughness, not way too much and not so little it can't grow into stars and galaxies. And I'm sure you've guessed my next statement. It turns out inflation provides exactly this. When you apply quantum mechanics properly to an accelerating expansion, it generates exactly the kind of roughness we need. In fact, most cosmologists view this as the greatest achievement of inflation theory. It naturally explains the origin of all cosmic structure. And I'll come back to that topic in lecture 32. Now, I want to end this lecture by briefly mentioning a fourth, rather more esoteric problem that is associated with the standard Big Bang. It's called the monopole problem. And historically, in the late 1970s, it was this problem and attempts to solve it that led to the theory of inflation, not in fact the flatness, horizon or structure problems. And it's mainly for this historical reason I want to mention it now. So stated briefly, the standard hot Big Bang theory predicts that the universe should be filled with rather odd particles called magnetic monopoles. They have the peculiar property of having a single north or south magnetic pole. Now, the reason the standard Big Bang predicts so many monopoles is actually a version of the horizon problem, but it applies not at the time of the microwave background, but at the time of the gut transition, at 10 to the minus 36 seconds. Here's that transition on our graph from last lecture of time versus temperature. Remember, the gut transition occurs when the strong force separates from the electroweak force. Now, when this separation occurs, for reasons that I don't have time for, magnetic monopole particles are created, one per horizon size. Now, at that very early time, the horizon size was a mind-numbing 10 to the minus 28 meters across. That's 10 to the 13 times smaller than a proton. So an enormous number of monopoles was made. Of course, they're diluted by the subsequent expansion, but that should still leave about one monopole per cubic meter in today's universe, which, because of their rather unusual single magnetic charge, makes them fairly easily detectable. But after many careful searches, no monopoles have ever been found, hence the monopole problem. Now, as you've probably already guessed, the solution to this problem is to have an early period of accelerated expansion. This effectively dilutes the monopoles, so there's only one in the entire visible universe, which of course explains why we've not found any. So let me review this lecture. The standard Big Bang theory is wonderfully successful in many ways, but it can't explain several key properties of the universe. It can't explain why the density is so close to the critical density. In other words, why the spatial geometry is Euclidean. It can't explain the cosmological principle. In other words, why the universe is so smooth on large scales. And it can't explain the origin of the slight roughness on small scales that makes stars and galaxies. As we've seen, the fundamental cause of all three of these problems can be traced back to the first moments, the launching of the Big Bang, if you like. The main problem with the standard theory is that it assumes an early universe, even back at the very beginning, was dominated by radiation. And with this assumption comes the inevitable expansion history. Infinite speed at time equals 0, followed by rapid deceleration, and it's this that causes the problems. Now, the assumption of a radiation-dominated universe is clearly valid back to at least a microsecond. But before that, we really don't know what's happening. And as I've tried to explain several times in these lectures, to nature, that first microsecond is an enormous tract of time. Lots of things could happen. So perhaps, at some earlier time, the conditions were different, with a different kind of expansion. In fact, what we're looking for is an expansion that starts slowly and accelerates. That's what's needed to solve the flatness and horizon problems and explain why the universe is Euclidean and smooth. But of course, it's one thing to suggest that the universe begins with an accelerating expansion, and it's quite another to come up with a mechanism that actually achieves this. Well, of course, that's what the theory of inflation does. It suggests that, at some point, the dominant stuff of the universe wasn't radiation, but it was something else, something that gave an accelerated expansion. In a sense, this brief phase provides a launching mechanism for the universe's expansion, exactly what's so clearly missing from the standard theory. So stay tuned for the next lecture and learn and find out how the universe's Herculean expansion got started.